Thank you very much for the introduction. So there are two things I would like to say before we start with the talk. And the first one is, what I'm saying, those are my own words. They do not reflect, of course, the opinions of any former or current employer. And the other thing is that I know that some people can react not in a good way to AI or diffusion-generated content. So any image which was generated by these means, it's marked with a star in the right top corner. But let's start with materials, because as Johannes said, I am a material person. I did my entire academic life, I did materials. I've never done anything else. It's quite a focused thing, but then I did everything with materials. And these days, it's kind of a good time to be a material researcher, because a lot of people these days are doing material research, and there is a strong focus on how to get materials more realistic. And in particular, these days, you can read quite often in publications things about high-quality assets and photorealistic materials. This is something we have used in the last 20 years quite often. Film-quality assets, film-quality materials is another thing. And as a person who worked in production for many, many years, who worked on a production renderer, these things, they're something which are very dear to my heart. And so as a start, I would like to share what it means to produce film quality assets, film quality materials. Because what we do see as the gold standard these days, it's materials, it's visuals from feature films. And the reason for this is because feature films, they aim to produce graphics which is indistinguishable from reality. So this is what we want to achieve. We want to have something which is not just plausible, which really and absolutely fools you in a way that you think it is real. The way it is achieved in VFX is with long iteration times, with a lot of compute and attention to detail. And normally, when I would ask someone, what do you think is a difficult material? What people would normally say probably is skin, and then followed by hair. And yes, this is absolutely correct. Both skin and hair are super complicated. But as a matter of fact, we spend a lot of time with both to get them in a state where they look really, really good. So less obvious, it's all the other materials which are there, which are the environment materials. And we have so many more materials we need to be able to describe, and which are actually very, very hard to describe. So if we have materials like fabrics or stones, vegetation, they have all a very complicated internal structure. Like there are fibers, there are multi-layered materials, there is porosity. It's really hard to capture that kind of appearance. And in fact, even offline rendering, what we think they have figured it out, no, they haven't. Even the VFX industry, for them, it's a lot of trial and error to get the material right. When I say getting a material right, it's always the question, what makes a material look good? When does it look good, and when does it look CG? And materials, real materials, they have some kind of, I mean, you know if it's good or if it's not good. You just implicitly know. So what we have is material complexity. Real materials are a complex thing. They have a variety of different effects. They will have micro sketches and small vents. They will have signs of wear and tear. There is variation, but the most important thing, this variation, it's not an arbitrary variation which is anywhere. It is done on purpose. The other thing that is there is never a sharp edge on an asset. What I mean with that is the sharp edge is the equivalent of the perfectly specular BSDF. It does not exist in reality because a Dirac impulse is something artificial. Sharp edges and round edges, they will produce a different kind of visual appearance. The round edges will do something different to the highlight, and the human eye is trained on seeing that and not the sharp one. Then we also have a lot of details in real materials. Details like dust or manufactured artifacts, very, very small details which you do not immediately see, but you still perceive them. And the way to do those would be with a high texture resolution. In particular, visual effects industry uses an insane amount of textures when it comes to building materials. The tool which is normally used to achieve this is called UDIMs. I've noticed that people from the games industry or academia normally do not come in contact with UDIMs. UDIMs is a way how you can split your asset, your object, into multiple different texture regions so that you can increase the texture resolution. Let's have a look now at how this particular T-bot is built up. Assets, materials, they are built like real objects. So you start with the clay as a base material. The clay will have some kind of normal map, which is a little bit hard to see on this projection, but believe me, it's there, totally. And then you put some kind of absorption layer on top of the clay. The absorption will cause a few dependency in the absorption so that it becomes more saturated at grazing angles. It's driven with a thickness map, so another texture, and then you put the clear coat on top to have your base ceramic. The clear coat, it's 2 dielectrics, not 1, so that you have more roughness variation in there, that you can do something like fingerprints, like stains, like smudges, something which gives you more visual fidelity. Then on top, we do then have something we call the imperfections. You will have water stains on top, like the smudges, something like diffuse BRDF, which is half see-through so that it roughens the dielectric below, and a couple of dust flakes because everything is somehow dusty and you also want to have those. So those dust flakes, they're super, super tiny and you wouldn't even see them normally if you don't look carefully. All the textures which are used here, and you can see it at the side from the individual BSDF layers. Every single of those squares represents a texture. So all of them are 4K textures, and the asset has 14 UDIMs. This means that every textured parameter has 14 4K textures which are on the asset, which is a lot. So these details we are seeing here, they are not arbitrary. It's not that people just put them there randomly and then they are there. No, they are there for a purpose because they need to tell a story. And it is sometimes harder to not do all these dirt and imperfections than to do it. It's always a question of how aggressive is it in the end. And so the keyword is well-loved and not necessarily dirty. For reference, so those stats, I took them from a paper because it's really hard to get production stats. The stats are from a 2018 paper, and you can see that I'm not making this up. In a classic scene and a classic frame, there are a lot of textures, there is a lot of complexity going on, and this is what we need to achieve. Materials, again, they are there to tell a story. We don't make them as complicated as possible just because we can. They need to serve a purpose. And this complicated thing, this is our means to adjust the materials. I really like to, when I talk about materials, to bring this example of why it is important to have this material complexity. Skin, how we would normally see it, like you have some kind of epidermis, which is the outer shell of the skin, and then you have some subsurface scattering, bulk medium, and that's your skin, and this is normally the skin we do in academia, in research, and it's great, it looks like skin, but it looks like the skin of a newborn baby, it looks like the skin of someone who has never seen anything. Skin, in reality, is not like this, because everyone has scars, everyone has bruises, tattoos, all these things. And just by changing the appearance of an object, of a character, you can give something a background. You can ground the object in reality, and you can give it a history. Depending on what you do with the appearance, you know if your character just exercised because it's sweaty or had an accident because it's bloody. So all these things, they play together and are very important. making production materials, it's not about making them as complicated as possible. It's also not making them as physically accurate as possible. It's always a mixture of different requirements. And in particular, in production, you need to have the sweet spot between performance, artistic freedom, and correctness. Because you still need to be fast enough to evaluate your frames, you need to be correct enough that it looks plausible, and you need to be flexible enough to give an artist the capabilities of expressing themselves the way they want. Today's material systems, they are almost exclusively layered material systems, like layering of BSDFs on top of each other, like I showed in the beginning. So why layering? Mainly, it's a convenient thing. It's a convenient thing of creating appearances, of creating materials. It's a natural way of modeling because it reflects our realistic workflows. You can build templates with the layers, but even more important, it's a non-destructive way of material design. It's because you can't adjust it with masks, you will never have your final material all in one. It's a different thing than having an Uber shader where you would bake all your material properties into specific texture maps. Layering operators are the cornerstone of a layered material system. We have classic operators like mixing and coating as a combination. There are a lot more, some more esoteric than others. Recently, there's also a lot of thick coat going on, which is taking proper refraction into account, bouncing between layers, but it's more like an exotic operation, which is not very popular. What we do is say, though, when we have a layering system, we can differ between horizontal layering operations and vertical layering operations. Horizontal, where you do not increase the size of your stack, and the verticals, where you do. What we fill the layered material system with are BSDFs. And depending on your material system, you can have a couple of them, or you can have a lot, like I did in Manuka. I did a rough head count in 2019, and I counted 172 different BSDFs and phase functions. This is a lot. 67 of those were really unique BSDFs. And by unique, I mean unique source code, unique appearance, standalone BSDFs, which would not have anything in common with other BSDFs. Of those 67, we had 54 surface BSDF, BTDF, BRDF, and then 6 fiber BCSDFs, 5 phase functions, and only 2 emissive EDFs. What we can see here is that we are a lot more concerned with the reflectance of materials of objects than with emission, because apparently no one cares about emission. 67 is still a lot. It's not as much as 172, but still a lot. In practice, it's not that you use all those 67 all the time. You have a core set of BSDFs, which you would use, and most of you probably here have seen those BSDFs I showed here. Those are the core BSDFs. It's a surprisingly small set, and it's absolutely not the latest and greatest in research. You can see that they have some time on it, especially the Lambert one. What they give us the sweet spot between usability and expressiveness. And much more important for production, they are battle-proven. It means that we exactly know what they do, we know how they behave, we know their performance. They are just our best friends. These canonical BSDFs, they are part of most, or actually I think all material systems. They will be in Material X. Material X is a layered material standard in the VFX industry. You will have them in Llama, you will have them in Unreal Substrate. It is the canonical set of BSDFs. Additionally, recommended, I would say, I would give a glossy, unrefracted transmission so that you can simulate something like diffusion through a thin material. View-dependent absorption, also very, very nice to have. A good fabric material is also something you cannot say no to, because that's the things these materials cannot do. Where material systems differ, that's the part where you have the crosstalk between the BSDFs. Because you can say, well, in its most simplest form, the BSDF is a standalone object. It's kind of black box. It doesn't know anything which is going around itself. But in modern layering systems, modern material systems, BSDFs, they will change their appearance depending on where they are in the stack of the materials. And in particular, we have two important operations, IOR accumulation and roughness accumulation. IOR accumulation means that the BSDF will change its reflectance based on where it is. So in this simple example, two dielectrics coated on top of each other, same index of refraction, which means they are index matching. The second one should, in theory, completely lose its reflectance. Without IOR accumulation, you can see two highlights. That's clearly wrong. With IOR accumulation, the second highlight vanishes. And similarly, roughness accumulation. The theory is that a material can never be smoother than the material on top. So you need to have the roughness transferred from the top to the bottom. And same game, the bottom highlight should be rougher than it is. It should not be specular, but it is. But with roughness accumulation, this is gone. More like a requirement, not a fancy thing to have, is how you decide which transmission you would have. This can become complicated if you have a couple of transmissive TDFs on top of each other. Which one do you use for the transmission? Do you take the bottom one because it was the last one in the stack? Then you would get the perfectly sharp refraction here. Or would you take the roughest one? So that's the first one. Or do you take a combination of both? It's really not easy to decide, because this is not a physical process we are emulating here. It's up for the designer of the material system and the artist to decide what to do. I mean, in production, it's kind of easy to say what is correct, because correct is always what the client wants. It's not about physics. It's not about what you want. It's about what the client wants and what the client expects. These examples, they look super easy and easy to decide what to do in the simple case. Believe me, once you get materials like I had with the teapots, it can become very, very complicated what to do. Key is an efficient computation, so what you do not want to have is combinational explosion, and you don't want to have a noise from stochastic processes. Okay, if we now compare this layering to the classic PBR material we have in academia and we would have in real time in games engines, for example, we can see that the PBR materials, the PBR BSDFs, they are a subset of the layered BSDFs and a subset of the layering what we do. They have the same components, the same canonical BSDFs most of the time, but they have a hard-coded order of how the BSDFs are ordered. And they are good at some things. I mean, we wouldn't use them if they would be bad. They're great at doing ceramics, at paint, hard plastic, rust, concrete. So a lot of materials, actually. But they're really, really bad when it comes to more complicated materials, like multi-layering, like fabrics, like, like porosity, all these things. They cannot be done with the simple PBR materials. Where things really, really start to break down is at grazing angles. It's very hard to get grazing angles right with a simple PBR material. So PBR materials, great, but they don't give us the fidelity we want if we expect the fidelity from visual effects. So when can we expect that real-time rendering catches up with the appearance of offline rendering? Generally speaking, there is a flow from, okay, you start with academia, you research something, and then you go to offline rendering, and then you go to real-time rendering. So there's a flow of technology. And till something becomes practical. And we have, for example, if we look at path tracing started in 1986. And if I look into this room, there are probably a lot of people here who were not born in 1986. It took 20 years until we had the first path-traced feature film. So generally speaking, normally people say the first one is Cloudy with a Chance of Meatballs. And it took almost 20 more years until we had the first path-traced AAA game. For layering, it's not as simple to pin down because we don't have the seminal paper which were introducing arbitrary layered surface combinations. We have a couple of them which we can say, okay, they were the beginning in the 1990s approximately, like Pat Hanrahan's paper here. Again, it took more than 20 years before we had a feature film which was using an arbitrary layered material system in a featured film. And even now we don't have a game, a AAA game, which is using layered material systems, although we are close. With Unreal's substrate implementation, we are close to having the first multi-layered material system in a game. The reason why technology transfer works is because algorithms, they become better, but more importantly, hardware becomes faster. And so you can get away with things you could not do before. But there's this thing, people say that Moore's law is at an end. So we cannot trust that the hardware becomes faster and faster the way it became faster until now. And this leaves us in a little bit in a pickle, because if we cannot trust that the hardware is faster, how can we expect that we have this kind of technology transfer? And that's the reason why neural is so hyped, because it gives us a way out of the end of Moore's law. And it's probably nothing I need to convince anyone here, because right now there's a lot of research going on about neural rendering, neural materials, neural everything. I did a very rough count of, just for fun, all the publications, SIGGRAPH Asia, self-titled reflectance modeling. So they claim they do surface materials, comparison between the analytical, the non-neural papers, and the neural ones. And what we can clearly see is that the analytical material research is coming to an end. Neural is picking up, analytic is going down. And we are right in the middle of the neural research academic phase. The neural material paper we published in 2023, it was neither the first one, it was also not the last neural material paper which was ever presented. The thing which makes it kind of a little bit special, I would say, is that it is the first paper which was targeting film quality materials. And by film quality, I mean the definitions I had in the beginning. To get those materials was a fun project. We were working with our artists together and asking them to generate a number of highly detailed digital assets for this project, with the requirements that the texture resolution is high enough that from 10 centimeters distance you would not see any visual artifacts. 4K texture resolution with as many UDIMs as they liked. Arbitrary layered BSDFs. In our case, we're using the Material X layering system. No displacement, because our renderer couldn't handle displacement that well, but otherwise as many textures as desired. And the material complexity we came up with, it's comparable to what you would have in VFX industry. We have deeply layered, multi-layered materials. They're composed of multiple BSDF lobes that represent physical layers, real physical layers. We have all the imperfections. We have the dust. We have the stretches. We have the stains, all these things. And the shaders you have, if you have these materials, they tend to be much slower to execute than those we normally use in real time when we have PBR materials. And to make things work, these shaders, they would all be different as well, so it means you will have a lot of divergence in URIs. when we evaluate a material for a given shading point, we evaluate the local BRDF of incident and outgoing direction. The most straightforward approach is then to feed those to an MLP, which is tasked to predict the corresponding BRDF values. And this is exactly what was proposed by Strachmann and colleagues a couple of years ago, and which we are building on. They focused on spatially constant materials. We want to have the textual variation here. So to support the variation, we followed another paper, and what they did, they fed an additional latent code that compressed the position of the BRDF attributes. It's kind of similar to the normal graphics pipeline. So these latents, they are fetched from a latent texture, and more specifically from a latent texture pyramid. And this means that the MLP output, it can predict a filtered version, a level of detail version of the BSDF. In principle, you could train this end-to-end with the sample texels and the directions, do a random sampling of the samples, and you backpropagate through the MLP and to the texture lookup, and you're done, which is exactly what they did in the paper. But this doesn't really work well with the materials we had in mind. So in particular, the texture size which were used in the paper was 512 times 512. And the problem is for a higher texture resolution, 4K textures, the one we had, it's problematic because the same sample budget is split between way too many texels, and so each one receives fewer gradient updates, and the optimization simply doesn't converge anymore in a reasonable of time. But we can still exploit the fact that many surfaces share a lot of similarity, and so we propose to replace the latent texture with an encoder network, and that one takes all the BSDF parameters we had in the reference materials, and we're feeding it to the training. And so this way, similar texels will automatically be mapped to similar latent code. And we can see that the result is a lot better by using the encoder. So the additional network we have here and all the BSDF parameters, they are kind of heavy and we don't want to have them during render time. What we still can do is we can still explicitly generate the latent textures, use those, completely remove the encoder for the rendering, and pretty much we are done. The paper goes way into more detail about introducing a shading frame decoder and to have important sampling, how these things were done. If you are interested, I don't think they are so interesting that I want to go through them now. If you are interested, read the paper, talk to me, one of these things. The more important thing is we have this decoder, and with the decoder, we can do nice things. For example, we can adjust the decoder size to change the quality and the performance of a material. Doing material LOD is something which is rather hard with analytical materials because we cannot form them, shape them to our liking, but it's a task which is very easy for a neural network. We have another asset here. This maybe doesn't look like it, but it is significantly more complex, like the Lund teapot we were seeing before. The reason for it is that it pretty much combines the complexity of the teapot and the handle of the teapot in the same material, because we have this blend between the metal and the ceramic at the same time. The asset, again, was built with Material X. In the end, we ended up with 9 BSDFs for the asset, and the asset had 6 UDIMs with 4K textures. So we can now change the size of the decoder to adjust performance and quality of the material. The numbers I have here in the upper corner, they show the total render time, not the shading time. It is a 2K frame, full frame material, rendered with a path tracer. But to be fair, it's just standalone, so the path tracer is pretty much a first hit only. So can probably ignore the past tracer. So what we can see, though, is that compared to the original material, compared to the reference material, the render time goes down. We settled to different quality sizes for the network. So we have the high quality, 3 times 64, the medium quality, 2 times 32, and the low quality with 2 times 16. And depending on the network size, performance becomes faster, becomes better, quality goes down. I'm pretty sure no one here can really see the difference between those different materials. They are there. You can see them when I start flipping between them. There is unquestionable a degradation in the quality. And I wish I could now say, well, everything works, and all you need to do is you change the size of your decoder, and it's there. It would be a lie, though, and we are not lying. So for the small networks, it is hard to train them when the underlying material is super high quality, super complicated. The larger ones, they don't struggle that much, but the very, very small ones, the 2 times 16, they have a hard time. And in particular, when I first tried to train this material, I was struggling with the normal maps here. The way we choose the samples, it's a mixture between uniform sampling and importance sampling, and feed those to the network. The network really didn't like it for the normal maps. Interestingly enough, by introducing more random noise into the data, we can get much better results than we had before. So suddenly, the grazing angles still work. We have good normal maps. What we did get rid of, what the network sacrificed, was the color tint in the absorption, in the grazing angles. Interesting enough, we can achieve this by doing something counterintuitive and make our samples worse than they should be. This means, in the end, I mean, the sad thing is there is no solution that will work for everything. It's a little bit of fine-tuning for a specific material, but the problem itself indicates that we need better sample distributions for the training, a better understanding of the sample distribution, what's good for learning, and or a perception-based loss function, because the mathematically ideal solution is not the solution which are the best suited one for training. What we can identify, though, is what is hard to train. Hard to train, my arch nemesis, specularity and normal maps at the same time. And not just specularity and normal maps, multiple of those. That's super hard to train. A little bit more counterintuitive, saturated colors, or finding outliers in your training data. I mean, this is a data distribution problem. How do you identify which part of the material are important and which are not? And my personal favorite, mixed materials, which is something artists really like to do, combine different kind of material in one single asset, in one single material, and then you need to learn a way, way more complicated material than it should be. But what I really want to point out is neural materials, they are not an academic fantasy, they are real. They are not a research concept. They are here and there, they will stay. In particular, we tested them on large scale scenes, and we tested them with an Unreal Engine implementation in a production game engine as a concept. For the large scene training, I was using the Da Vinci scene. Da Vinci scene is a scene which NVIDIA published free. Everyone can use it. If you want to have a scene which is production-like, this is probably the best you can get, because it has over 1,000 different materials. Even if I deduplicate the materials, I end up with more than 500 different materials. The only drawback might be that the materials are MDL materials, so it means omni-PBR, omni-surface, and MDL is not something which we would normally use in research. So 500 materials, this is a lot of things we need to train, even if you have fast training time. And our training time is it's a couple of minutes, 2 or 3 minutes per material, went way down from the hours we had in the beginning. It's still a lot of things you need to train. The thing is, do you really need to train all these materials separately? Because if you look at scenes, they share material properties, they share appearances. And so the question is, can we train materials to utilize that? And yeah, we can, because we can cluster materials into groups we want to train together. So this is a small subset of assets we have in the Da Vinci scene. And we can see there are certain similarities. So we have, for example, very specular metal materials, or diffuse-ish gray, something like the log and the ash, or the wood. All the wood assets, they look pretty much the same. Not so much for the statue or for the flower pot, but you don't need to put everything together. First, just by clustering some of the material, you can save training time, you will reduce divergence, and you will reduce the render time. There is a stop, there is an end, what you can train together though. For example, if I take the door, I've trained it 3 times. Once it has 4 materials, the wood, the 2 stones, and 1 metal. And first one is I trained everything separately. Second one, I trained the wood on one end, and then metal, stone on the other one. And the third one was just everything all together. Again, it's a little bit hard to see here. I can flip between those. There's also an error image. What we can see is that the spec of the wood starts to change a bit. So the more materials you put into your training, the worse the training will become. But again, you don't need to train everything all at once. You can still cluster these materials separately. And this brings us to the next question. How can we decide what to train together? You don't want to have the network becoming larger and larger and larger, because this means the render would become slower and slower. What we need the sweet spot between the size and the expressiveness of the network. And so you can cluster the materials together according to their appearance. I would not advise to do it according to material categories like leather or wood or stone, because 2 leathers can look quite differently, whereas a plastic and a painted lacquer look very similar. So we need a redefinition of appearance here concerning which features can be learned together. Future research, I don't have the solution. But what we can say at this point is, so we have on the one hand, we have the analytical materials, our traditional materials, and we use them because they have existing workflows and DCCs. They are easy to edit, even on a very fine granular level. We can use them as prior for training, and we can use them as training data itself. And on the other hand, the neuromaterials we have so far, they are baking solutions. They can encapsulate data very, very well. They can do things like automated quality approximation, level of detail simplification, compression of shaders and compression of textures. So all these things which are very hard for a human and very hard to do with analytical materials. We are not, with the neuromaterials we have, we are not replacing analytical materials. We work with them and we use them as an underlying base for the neuromaterials. Next question, which normally comes up then, is, well, can we completely, I don't like analytical materials, can I completely get rid of my analytical materials? Yeah, people do it. I mean, this is what differentiable rendering is all about. It's about getting the data from a diffusion model, for example, instead of creating it manually. You can do it from single photos, you can do it with intrinsics, with prompts. There's a variety of different ways how you can generate materials other than from within a DCC. But the problem they all share is that as long as there is inverse rendering part in the pipeline, there's almost always a simplified BSDF model which is used for the optimization. And in particular, this PBR material I showed right in the beginning is one which is used very, very often. The problem here is you are only as good, your results are only as good as your base material. And if the base material cannot capture the effect you want to do, it's simply not possible to learn it. Don't get me wrong, it's not bad what you get with these materials. So teapot here, one is the original one, the column to the right is the simplified one. So we are losing we're losing the orange peel of the top glazer, for example, or we are losing the view-dependent edge tints, or just the fine structure we have in the original one, in the original teapot. Again, it's not really bad, but it's not a faithful capture of your material. So, okay, if there is a bottleneck between what we can get with inverse rendering from the analytical materials, can we then maybe completely get rid of the analytical materials and completely ditch them? Can we do fully image-based rendering instead? Well, I mean, you have to acknowledge that diffusion-based images, they became better and better. They improved over the last years. I remember everyone made fun of the 6 fingers and the 3 eyes people had. It's not there anymore. The improvements we saw within the last years were just amazing. So there is definitely a potential to create images far more realistic than what we can do, what we are willing to do with traditional 3D graphics. And especially video models, they show a great potential for us to enhance the graphics pipeline, which raises the other question: is it time for us to ditch physics and simulations? Do we still need to understand the theory behind materials, between light transport? Should we, as a graphics community, stop teaching these things? And it depends on your view on where we are going with this technology, if these things are necessary or not. Because a lot of people also talk about using the video, especially the video models, to replace the entire graphics pipeline, the entire production pipeline for games, for films, and use instead a video model instead. What people tend to ignore who never worked in production is that this image generation is really just a very, very small part of the pipeline. It's right at the end, the rendering, and everything else before is a huge part of movie production. It's more importantly, it's not a linear thing that you say one person begins and then it goes down until we have the rendering, until we have the comp, and we are done. Now, it's an iterative process. Creating assets, it doesn't take, or creating movies itself, it doesn't take long because people are lazy, they don't know what they are doing, or that the actual craft takes long. The reason why it takes long is that we have those revision cycles, that you start with something, then you show it to someone else, and this person will kick it back to any part in the pipeline, and then you need to start again and again and again. And this goes on and on. As a rule of thumb, frames, they get never finalized because they're perfect. They get finalized because you ran out of money or you ran out of time, but not because they are perfect. So this obsession with revision is also why people normally say, okay, there are 2 things which are the make or break for image generation, a complete replacement of 3D rendering. So the controllability and the consistency. The controllability. Can I address a note, for example, that the specula from the 3rd character to the right should be a little bit tighter and just change that, but nothing else? And the consistency. Can I generate the same thing twice? Can I generate exactly the same asset, but once with water droplets and once without? So those are the things people say, okay, we need to be able to solve this. The truth is, it really depends on the director and the artists and how they like to work, because I've seen people being quite happy with improv. Let's say it's something like you would have 2 actors reciting a dialogue 100 times, and the director just picks one because it likes it. That's the equivalent of prompting. You just try, and then you get something you like. And then there are other people who have a very, very, very focused vision, and they want to have exactly this one thing they have in their mind, and there is 0 wiggle room for anything else. What I want to tell you is just the way people work, it's different, and not everyone is the same. There is no one-size-fits-all workflow that will work for everyone, and the technology needs to adapt to different workflows. It's definitely not the other way around. Technology follows the artist and not vice versa. The artist does not follow the technology. But I know people like lists and wish lists and all these things, so this is my very, very personal wish list of things which need to happen before we can see the visual fidelity we know from visual effects with the image generation pipeline. And one thing is resolution. 4K, 8K, stereo, EXR images. And please don't tell me, well, we can res them, because that's not exactly the same. It always looks different. Masks way beyond what we have right now. Not just segmentation. We need masks, things for like, well, the heat pattern on the exhaust of some spacecraft, and just this one and not the other one. So very fine granular things to adjust. Deep data, and I don't mean the depth bus, I mean volumetric deep data. Things that are standard in compositing, because at the final frame, the image you see in a film, it's never directly coming from a renderer. There's always a comp department which is doing the adjustments on the image. It's also normally not an all-in-one render, where you would see everything rendered at the same time. People render in layer so that they can iterate on specific assets, on specific looks. The third thing is sharpness, crispness. Softness is amazing for Instagram. It's not necessarily great for realistic images. And then lastly, I can easily make a movie girl in a coffee shop. Creating a girl in a coffee shop with diffusion, it's amazingly easy, because these systems are trained with this kind of image. But life itself, life is raw and life is brutal and life is not pretty. And we need to be able to go beyond this kind of prettiness of everything is bedlick and everything has a shallow depth of field. So in a way, I don't want to say it, but ugliness. We need more ugliness. But again, this talk is really not about us answering the question, is rendering that? I'm a material person, and so I'm interested in analytical materials. Are analytical materials dead? Do we need to stop doing research about them? Do we need to stop thinking about those? And I would say it really depends. Who's the audience? Who's asking the question? Yes, I dare to say analytical materials are dead for fast graphics. And by fast graphics, I do not mean real-time rendering. This is not about real-time versus offline. Fast graphics is fast image generation in a way of iteration times. It's content creation with fast iteration time, like advertisements, product design, architectural design, the 5 minutes YouTube clip you see somewhere, or the 20-second TikTok you watch on your screen and you don't even look at what you're watching. So for this kind of applications, yes, I say analytical materials are dead and no one will use them. The other end of the spectrum, predictive rendering. And here I can say no. I do not think that we will replace predictive rendering with any video model or any diffusion models, because here it's about predictability, and it's of the uttermost importance to be able to say this is correct or this is not correct. And it's hard enough to keep track of the error, the normal error you have in your render pipeline. I really wouldn't want to have a model in there which is hallucinating data, which I cannot control at all. And then in the middle, you have the slow graphics. Again, not offline rendering, but slow, I'm talking about the process of developing something. And here, I think we have room for both. I think that analytical materials and neural materials can happily live side by side. Then we can use neural materials, neural generative processes to create materials. And on the other hand, sometimes it is just easier to use traditional workflows because, for example, the material you have in mind is not in the base data your model is trained on. So you can use your traditional knowledge for those. In the end, a user, an artist, It will always use the tool which is best for the job. And so if Analytical is best, you take that. If the other one is best, then you take that. The truth is, though, no one really knows. For a while, we had this thing that predictive rendering would become more and more, and people were going from, oh yeah, physically based, this is really, really cool because I can control it so much better and it's more expressive. And then we had this 2017 microfacet wave optics hypes, and then suddenly, yeah, okay, now we have diffusion and materials, and we don't really know what's going on, and we don't know what the future will bring here. What we do know, though, is that the first time ever real-time rendering, real-time graphics, and offline rendering, the development is in sync. There is no longer, okay, we have offline rendering as the test bed for real-time rendering, and then if something is proven and the hardware is fast enough, we're going to real-time rendering. This is not the case here. Neural materials, neural technologies, they are the same for both real-time and offline. And so real-time and offline, they go hand in hand. In the end, again, no one knows what's happening in the future. It is an exciting journey we are on, and only the future will know what it will bring. And with that, I think I am in time. Am I? Thank you.
Thank you so much, Andrea. Are there any
time?
Yes. I mean, yeah, so we ran a bit over time with the paper session, but that's fine. We have enough time for lunch, so we'll take our time here. No need to get nervous about that. So any questions?
Thanks so much for the talk. That was absolutely excellent. Like with like dust textures, I can't imagine how sparse that is as a texture. But I don't want to talk about representing it as texture versus geometry or particles. But how do you measure the perceptive importance of those dust particles? You can't really measure saliency. It's more of a global impact on the end user. So I was just curious if you had any comments about that. And did you have any perceptive quality measurement for the importance of subtle effects such as dust particles?
It's a good question. It's an open research question. There is nothing where I can say, yes, of course, we have the answer to that one. Right now, it's an explorative session of figuring out what works and what doesn't work.
Nice talk. It was quite informative of how production works. So how easy would it be to start with with explicitly modeling the statistics or explicitly modeling the microgeometry procedurally, and then training the materials to then approximate the results as you zoom out on them?
Great question. I think it's a very feasible approach to model something explicitly and then create your BSDFs out of that one. The main bottleneck is, of course, the modeling, because what I didn't mention is that modeling assets, modeling materials, it's a very, very time-consuming process. And even if you do it procedurally, you are then back at the problem of it is not an arbitrary thing. You would still need to drive it with more information, for example, coming from simulation, where should be what, where would I have wear and tear, where would my microfacets be different than in other places. So from a technical point of view, yes, I think it's very feasible to do. From a content generation point of view, this is most likely the bottleneck you will have.
Any more questions in the audience?
Thanks. What would you say is the place of photogrammetry and capturing materials from the real world in all of this?
Another great question. I think it's it fits right into this world, using photogrammetry as a source of data. We, as material people, we always struggle with where we get our data from. For the image models, for the video models, it's kind of easy because you can skim YouTube, you can skim the internet, and you get your data. But we don't have the data for materials, because measuring materials is a very time-consuming process. Simulating them from ground truth is even more complicated. So getting the data from photogrammetry is, at this point, very good. The question is only, how can we extract the information we really need?
Hello. I thought what you said about needing things to be uglier, that's a very interesting and I think very salient point about all this generative AI stuff. So I was wondering if you had any ideas about how you would improve the training sets for these generative models so that you can get more flexibility in sort of the aesthetics and maybe even like art style of what you want to generate?
So my disclosure, I'm not a generative AI researcher. So everything I say is take it with a grain of salt. I think the problem is that in the past, models were trained with materials from, based on being rewarded for creating pretty images. So you need to change the reward process, because I still believe that there is so much ugly data on the internet we could use for training, where it's amazingly easy to produce a burger, for example. I get surface details which are incredible if I zoom in into the image. I cannot get the same kind of thing for something like fabric. It always looks kind of off, because a lot of people most likely did photos of their burgers and put them on Instagram, and so we have the training data for that one. Ugliness, again, I think the internet is full of ugliness in the best and the worst ways. It's just rating the data correctly.
Hey, thank you for amazing talk. I'm interested when you're talking about level of detail and having smaller networks and introducing noise to reduce the perceptual, to improve the perceptual quality. How can you share some thoughts on how introducing noise to normal maps or things like that, and how you avoided some sort of what sort of problems or things that you have to do to avoid problems, introduce noise into directionality? Or
so as I said in the beginning, if you have those super complicated BSDFs and you have this very tiny network, you want to fit everything. It's a oversubscription of the network, and you need to feed the right kind of data. You need to communicate to the network the kind of data you want. The noise I introduced, it was like I'm personalizing the network now, but it was running along and training, and then you take a wrench and you put it between its legs and it stumbles and it learns something else. The noise was a way to weight down, I think it was a way to weight down the important sample to peak, and so it had less of those samples and could concentrate more on other things. So for this one, we need to understand what is good, where it's focusing on, and it's also the reason why I say the loss functions we have right now, and we are using L1, it's not necessarily the one which is best suited for the task, and that we would need more information, that we will need more information about what is visually good and what is not as good.
Any more questions for Andrea? Yeah.
Thank you for the talk. I really enjoyed it. I'm not a material person, so this might sound like a dumb question. It feels like every studio or production company probably has a magnificent library of textures they've created. Do we feel like maybe having an open, or there may already be one, library, and then training on that open library would help solve the generative AI problem?
It would be amazing if we could do this. The main problem here is the data doesn't belong to the studios, it belongs to the client. And this would mean, in particular, Disney, Paramount, Warner Brothers. And so it's not the visual effects studios like Weta, ILM, DNEG, and all the others you need to convince, it's the clients. And they are normally reluctant to give something away for everyone if it's their own.
A great presentation, Andrea. I have a question looping back on the aggregate materials you were saying that are the hardest in visual effects in a way. Doesn't their appearance depend also on the light transport? I'm talking about hair and how you resolve that, and same with sand or whatever, a sandstorm or whatever. How would you approach that with neural rendering, and how would you create a material that without knowing what the light transport simulation is at that stage?
So the materials we have, they are trained in UV space, and they don't know anything about light transport. So they will always try to be they will try to do the best they can with the worst, assuming the worst light transport situation you have. You could think about saying, okay, I have my material, I know it will always be dark in a specific room, or the light will be diffuse, and you could start baking this kind of information in. But the reason why physically based material were so convenient is because you don't need to have this kind of information. You can train it once, you can take it, and you can put it everywhere. If you think of things like porosity, hair, those materials are volumetric materials. And if you would want to have the entire, something like neural radiance caches, where you have the light transport also baked in, then it's a different kind of technology. It's not what our neural materials do. I'm always a little bit reluctant to recommend taking too much focus on the light transport, because I'm a material person, not a light transport person, and I always say someone else can figure it out.
Folks, let's thank Andrea again. Thank you so much. Yeah, so now we'll wrap up, and so I'd like to ask whoever does that on stage. Thank you.